So this video is regarding CML102 assignment 1, which has 3 parts. For each part we are required to record a video, and then we are required to upload a video of all 3 parts in the form of one single video. In the first part, which is to identify the point group of the crystals given by sir in class, we are expected to record a video of length 5 to 8 minutes. For the first part, in order to identify the point group, we need to know that the crystals are rock sugar crystals, also known as mystery crystals. Rock sugar consists of sucrose molecules, C12H22O11 molecules, which crystallize generally in 2/m. Point group are essential in determining the symmetry of molecules. 2/m point group would mean that the 2 signifies a two-fold rotation. That is, for a particular lattice point, if we rotate the unit cell by 180 degree, we observe another lattice point at that place. This by m means there will be a mirror plane which will be parallel to the circle which we draw while drawing its stereographic projection. Now this point group 2/m is suitable for prismatic morphologies. If we see its macroscopic structure, if we see one unit, we observe transparent structures, and these transparent structures would mean their dispersion is possible and prismatic structures are prevalent. In the microscopic image which I obtained from Google Images, a lot of colors can be observed, which signifies the fact that dispersion of light takes place and all the colors can be observed. Also, all these colors tell us that after 180 degree rotation, the possibility of getting the same lattice point are possible. This is because of the structure of prism. Upon mathematical analysis of prism's structure, we observe that a two-fold symmetry can be seen in the way it is shaped. Also, the geometry is monoclinic, which is clear from the macroscopic structure of these rock sugar crystals. If we see the stereographic projection of 2/m, we see two lattice points. One lattice point, if we take as the standard lattice point, the other lattice point can be obtained by 180 degree rotation of this lattice point. This by m, the other part by m, means that parallel to the plane in which the circle lies, if we see parallel to that plane, we'll find two other point groups. This can be understood this way, that these solid dots, they signify lattice points above this plane, and these hollow dots signifies lattice points below this plane. So here, this is the stereographic projection of 2/m, and this is the Loewe projection. Also, since we could observe the structure to be monoclinic, we have also given the monoclinic unit cell, in which the cell lengths are different, ABC, and the angles alpha, beta, gamma are different as well. So here we justified the point group 2/m for this rock sugar crystal. Other point groups like 2 to 2, 2 by mm, etc. are also possible given the fact that all of these hold for the prismatic structure of rock sugar. The most appropriate point group I found was 2 by n. Thank you. For the part B of the assignment, which says that we have to record a video for the crystal structures of various compounds, the structures for which we drew using the software Vesta by editing the CIF file of the crystal PATiO3 given to us as the standard file. For starting with the file of PATiO3, the lattice type is primitive, space group number P1, setting number 1, lattice parameters is written here, 3.9 in general, a bit variation with C, and the fractional coordinates of different barium, titanium and oxygen atoms. This was the standard structure given to us, and based on this we are asked to record the crystal structures of various compounds using Vesta and also to explain this structure. The first compound we made using software Vesta is that of calcium telluride, CaTe, which resembles rock salt structure. The structure looks like this, in which we see each calcium atom is coordinated to 6 tellurium atoms forming a 3D arrangement, which is similar to NaCl. What happened in NaCl is there was Na atom which was surrounded by 6 chlorine atoms. The cubic arrangement was similar. Rock salt, since this is a rock salt structure, it would exhibit high ionic character and a simple cubic symmetry. The CIF for this is like this, where we edited the lattice parameters as 6.35, 3.99 and 4.1, and the fractional coordinates depending upon the positions of Ca and Te. The fractional coordinates are basically 1 by the x-intercept, 1 by the y-intercept and 1 by the z-intercept, and then getting the fractional coordinates. Then we move on to gallium phosphide, which exhibits a zinc blende structure. Okay, so zinc blende structure consists of zinc and sulfide molecules, in which we see a face centered cubic symmetry with gallium and phosphorus atoms occupying alternate tetrahedral positions. Each atom is tetrahedrally coordinated, providing a covalent bonding character. This is typical of semiconductors, and thus it has high symmetry and stability. The little variation which we observed in it is because of the different parameters, the different ABC we took, and that we obtained from Google after analysis, as the structure were monoclinic. This is for gallium phosphide. The unit cell parameters are 5.44, 3.99 and 4.1, and the fractional coordinates are written here. Moving on to the next structure, which is of K2O, which resembles an anti-fluoride structure. Here, oxygen atom occupy lattice sites, while potassium fill the interstitial positions. So the FCC, the face centered and the corners are taken up by oxygen, and all the tetrahedral voids are filled up by potassium. Since this is ionic and it exhibits cubic symmetry, the next structure is of CeO2, which resembles fluoride structure. For CeO2, we see face-centered cubic unit cell with cellurium atoms forming the cubic lattice. As we can see here, these are the cellurium atoms, and the oxygen atoms occupy tetrahedral interstitial sites. Here, and outside as well. This would be a part of another unit cell if formed here. These would be a part of another unit cell if formed here. This would be a part of unit cell which can be found here, etc. The CIF file for this is written in this manner. The lattice parameters are 5.41, 3.99 and 4.1, and the fractional coordinates which give the structural parameters can be stated here. We can see cellurium takes the base, the origin coordinate for the fractional coordinate, and oxygen takes up the tetrahedral coordinates, the coordinates of the tetrahedral voids. Then we move on to the fifth and the last structure, that is a structure of AuZn, which is a simple CSCl structure. We see gold atoms and zinc atoms. Let's go to this CIF file. Okay. It's a simple cubic structure with alternating gold and zinc atoms along each axis. Each gold atom is centrally coordinated with a zinc atom, creating a 3D interlocking structure. It is known for its cubing packing, and it's highly stable and symmetric. We can see the lattice parameters to be 3.19, 3.99 and 4.1. A little variation due to practical circumstances. Some variation would be due to the interaction between these two gold atoms and gold zinc atoms. These atoms would behave differently, and there would be a bit variation in the lattice parameters, which can be seen here. The structural parameters are here. You can clearly see that for zinc, the XYZ coordinates are 1 by 2, 1 by 2, 1 by 2. Thank you. So this is the video for part 3 of assignment, which is generating PPTs on the topic X-rays. Basically, we took the text from textbook Girolami. Some of the images are also taken from Google Images. Now, introduction to X-rays. Okay. So X-rays are electromagnetic radiation with shorter wavelength than visible light. If we see the spectrum of light, we observe that X-rays are among those radiation which have the smallest wavelengths. Radio waves have even smaller wavelength, but X-rays have smaller wavelengths when compared to visible light. They were discovered by German scientist Wilhelm Röntgen in 1895. Commonly, X-rays are used in medical imaging, crystallography and material analysis. How it is used can be analyzed if we know its physical and chemical properties, mostly physical properties. So it can be used in medical imaging because it can penetrate through the skin since its wavelength is very short. Other properties which tell us the characteristics of these X-rays will be studied sooner. The basic principle of X-ray generation goes like this. So here we have setup for generating X-rays. What we do is we take a metal tube and we have anode on one side and the cathode filament nearby. There is also a coolant from which water comes out in order to cool down the system, since a lot of heat is generated in the process. The water comes in here and goes out here. So this is the metal body. What happens is we strike electrons on the metal body and those electrons lose energy. That energy is observed in the form of X-rays. Now, generally we take either tungsten or molybdenum. We know that we can see tungsten in light bulb also. So, we can think that the thing which will come to our mind after listening tungsten is light bulb. So there can be X-rays in light bulb if electron would have been striking tungsten surface. Now, radiations in the form of which X-rays are observed are classified into Bremsstrahlung and characteristic radiation. Bremsstrahlung is rather continuous, however characteristic radiation is rather discrete. As we can see in this diagram, the characteristic radiation is discrete at some points of wavelength. That is, we observe this radiation at some particular wavelength. However, the Bremsstrahlung radiation, also known as white radiation, is rather continuous. It is observed as a spectrum of different wavelengths. Now, the spectrum consists of sharp peaks in characteristic radiation. These terms K alpha and K beta will be introduced shortly. Also, one more thing we can see is characteristic radiation are way more intense than white radiation, since the intensity which are corresponding to these peaks are more than the intensity corresponding to this continuous spectrum. As already stated, Bremsstrahlung radiation, also called breaking or white radiation, is created when high-speed electrons decelerate near atomic nuclei. What happens is we accelerate electrons between cathode and anode, and when it strikes the metal surface, it starts to decelerate. It starts to undergo a negative acceleration, due to which it loses energy, and that energy is emitted in the form of X-rays. This is a continuous spectrum due to its deceleration, and this spectrum is called Bremsstrahlung radiation. Coming on to characteristic radiation, as already stated, characteristic radiation is rather discrete. Emission of X-rays when electrons fill inner shells during electron target collisions. If electron would collide with the atom and it would fill the inner shells like K shell, L shell, M shell, if it would fill these during these collisions, the rays which are emitted is characteristic radiation, and it is dependent upon the level which the electron reaches when it hits the metal. It goes near the nuclei and thus it penetrates through different shells, and while penetrating through the shells, the radiation which is released is called characteristic radiation. However, the radiation which is observed when the electrons decelerate while striking the surface. That is called Bremsstrahlung radiation. Now it's time to explain what are these K alpha, K beta, K gamma and L alpha, L beta. Okay. So, if the radiation which is emitted, what we do is we observe the wavelength of the X-ray which is emitted. If that wavelength corresponds to the wavelength of light which will be emitted, if there is a electron transition from K2 to K1, then that is called K alpha. Actually, it is basically about transition to this beta shell to the alpha shell. However, beta is corresponding to the transmission from beta to this last inner shell, and gamma refers to the transition when it is from the outermost inner shell to the innermost inner shell. L alpha, L beta corresponds to the transition which takes place to the second shell. We can see that K alpha takes place if it goes from the second shell to the first shell. K beta when it goes from the third shell to the first shell. K gamma when it goes from the fourth shell to the first shell. L alpha when it goes from the third shell to the second shell, and L beta when it goes from fourth shell to second shell, L gamma when it would go from fifth shell to second shell, and so on. We can also define M and N lines like this: K lines, L lines, M lines, N lines, and so on. X-ray absorption. Now, X-ray absorption occurs as these X-rays pass through materials. When they pass through these materials, they tend to attenuate. There is an increase in absorption due to element-specific electron binding energy. There is some electron binding energy which elements possess, and in order to take this electron away from it, like when this electrons, this is the energy which is required in order to take away the electron from some particular shell. Now when an electron comes to a shell, it brings forth that amount of energy with it. Now that energy has to be emitted back, right? And that energy is emitted in the form of X-rays. So this sharp increase is dependent upon the binding energy, which is a function of material, which varies from material to material. This is the graph for percentage absorption versus wavelength for absorption of X-rays by copper. This is the K beta wavelength. This is K alpha wavelength, approximately 1.5 and approximately 1.38 something. And we can see the lambda H is lesser than lambda K beta. It is also lesser than lambda K alpha. Okay. Synchrotron radiation. Now this type of radiation is observed when X-rays, which are produced by the accelerating particles, let those particles be not alone electron, those particles can be any charged particles. When those accelerating particles decelerate, we observe X-rays. Now by certain accelerating particles, if they undergo deceleration by a very large amount, we can observe intense X-rays. That is, they move with a very high speed because they would have a lot of energy when they are intense. So when they move near light speed in a circular path, the radiation which is observed, the X-rays which are observed are called synchrotron radiation. What I mean is, if the charged particles, they accelerate near light speed, that is, they accelerate way too much in a circular path, the radiation which is observed, the X-rays which are observed, are called synchrotron radiation. Now the characteristics, as they can be predicted, as they can be estimated, as they can be conjectured, they can be guessed, that they will have high brightness because they are very intense X-rays. They'll have tunable wavelengths and they can be used in advanced research for knowing the advanced properties of different materials whichever these electrons hit while moving in these circular paths. The spectrum is like this: intensity versus energy for synchrotron radiation. We observe one point where it's maximum, and that is the point of critical energy. At this energy, the intensity is maximum. The highest brightness would be observed for this particular energy, which is 2 for some particular material here. The references are Girolami, chapter 13, and Google Images are used for some images and diagrams. Thank you.